Chapter 14, Chemical Kinetics. The speed of which reactants take place is called reaction rate. Reaction rate. So in the reaction rate, the unit for reaction rate will be molarity per second. So you'll be studying here the rate of the reaction, the rate the reactants are being consumed and the products are produced. Okay. And the study of reaction rate is called chemical kinetics. Chemical kinetics. In a step-by-step view of the change of reactants to products is called a mechanism. So there are different factors that may affect the reaction rates. For example, physical state of the reactants, so the more readily the reacts collide, more fast they react. So the physical state of the reactant. So homogeneous reactants or homogeneous reaction, let's say all gases or all liquids, they are often faster. In heterogeneous reactions that involve solids are slower. So the faster of these reactions occurs if the surface area is increased. And that's like finer powder reacts faster than tablet, for example. So if the reacts they're all in the same state, gases or liquids that are usually faster. So, and if you have a solid, you have heterogeneous reactions that involve solids are slower. But smaller the particles, faster will be the reaction because the surface area is increased. So this is what affected how the physical state may affect the reaction rate. The second factor that it may affect the reaction rates, it is reactant concentrations. So let's go back here. Reactant concentrations. Okay. So that means increasing reactant concentration usually increases reaction rate. So because you have more molecules, so you have more collisions. If you have more collisions, right, the reaction rate will increase. So faster will be the reaction if you have more collisions. And when you may have collisions, if you have more molecules, that means increase the concentration of the reactants, usually increase the reaction rate. And another factor, it is temperature. So reaction rate usually increases with increased temperature. So kinetic energy of molecules is related to temperature. That it means increase the temperature, we increase the kinetic energy, and increase the kinetic energy. The molecules will move more quickly. That it means we increase the number of collisions. So we go back to collisions. So more collisions, more collisions between the molecules, faster will be the reactions, right? So it's what it says here. At higher temperatures, molecules move more quickly, and increased number of collisions in the energy of molecule process during the collisions. Another factor it is presence of a catalyst. So catalysts affect the rate without it be consumed in the overall balanced equation. So, and catalysts affect the kinds of collisions, change the mechanisms. So mechanisms, what is? Mechanism is individual reactions that they are part of the pathway from the reactants to products. And catalysts are critical in many biological reactions that they are the enzymes. They are involved in many biological reactions. So catalysts affect the reaction rate and they are not consumed. What that means? You add a catalyst in the reaction, and after the reaction is done, the catalyst should not be consumed. So you can reuse the catalyst again for another reaction. Okay, so let's go to reaction rate. So, but how can you calculate the reaction rate? So reaction rate is change in concentration over time period. So the delta here means changing. Okay. Change. The brackets means concentration. So that means change in concentration. So this portion here. That means concentration change. Divided by, so this slash is division, right? Over time changing. The changing in time. And the unit for time, it should be in seconds. So let's go back here. The unit should be in seconds. The unit of the time should be in seconds, and the unit of the concentration should be in molarity. In molarity, it is mole per liter unit, right? Okay. Now you have here this reaction. Chlorobutane plus water producing butanol plus hydrochloric acid. Butanol plus water plus hydrochloric acid. The rate of your reactions is measured using the concentration change for a reactant or a product over time. So are you seeing here? Changing. So the rate is equal the change of chlorobutane divided by delta T. And why you see this, the minus here? Minus changing. Minus changing. The minus is because the reactants are being consumed. So this chlorobutane is a reactant, right? And it's being consumed. So that's why you have a negative here, because we're going to be final minus initial, and it should have, in the end, it should be a positive value here. For example, here, let's calculate this range here. This concentration, using the time from let's calculate the average rate that it happened in the first 50 seconds. So let's read it here. What was the final time? So let's go minus in front, right? The final time in here was what? In this region here, 0.0905 minus what? 0.1000 divided by the first 50 seconds, right? 50 minus 0, gonna be 50 seconds. So this, it is in seconds, and the unit here is molarity. The unit is molarity, right? And then we're gonna do this division here. Minus divided by 50, it is what? You should find this value here, right? 1.9 times 10 to the minus 4 molar per second. And if you calculate the next one here, that should be, so the second average rate is between what? Is showing this point for this two, right? If you want to verify to confirm, you should get it. Should be this minus this divided by 100 minus 50 seconds. Remember, the unit should be, the average should be molarity per second. Okay? So, and what we have here, right? The types of rating measure can be average rate, instantaneous rate, and initial rate. What is each one? Are you seeing here? This plotting rate data. The plot of the data gives more information about the rate here. So the slope of the curve at one point in time gives the instantaneous rate. So if you have question here in the specific point, specific time is called instantaneous rate. For example, here, if you need to calculate this area here, UB instantaneous rate here, because this point here is find it to at 600 seconds. If the instantaneous rate at time 0 is called the initial rate. So we have here, it's often the rate that interests to chemists is about the initial rate here. That's be the time equal to 0. So rate is dependent on stoichiometry. For example, if you follow use of chlorobutane in comparison to produce of butanol, butanol, the values would be the same. Why? Because the stoichiometric ratio here, look here, is 1 to 1, right? 1 chloropentane and 1 in here, butanol, right? So the rate of the reactants minus E because it's reactants is equal to the rate of the butanol, because the rate, stoichiometric rate between them is 1, 1. So if you follow the use of chlorobutanol, chlorobutane, and compare with it to produce of butanol, the values will be the same, but the only change is the signs, because one is being consumed, the reacts are being consumed. That means the reacts will disappear, and the products will be produced, will increase the concentration of the reaction is passing. Now, let's understand a little bit more about relative rates and stoichiometry. So we have here from ozone to oxygen, right? 2 moles of ozone producing 3 moles of oxygen. So the rate here will be the ozone equal to oxygen, right? But will be minus 1 divided by 2 here, because the coefficient of O3, you have 2 O3 here, so it's going to be divided by 2, equal to the produce, equal to the products. The products here, it is oxygen, and we have 3 moles of oxygen right here, right? And this is minus because it's reactant. And this side is the product. Let's go to the next one. Next page here. Next page is about problem 1. Sorry. Problem 1. So for problem 1, and from the data, this picture here, you have, let's say that you have here the volume is 1 liter, right? So that it means 1 mole of A, 1 molar of A, and you need to have A and 0B. So the reaction will be, let's say, A is the reactant, B the product, right? So 1 molar of A, I'm calling molar because let's assume that the volume is here is 1 liter. So it will be 1 molar of A, and the time is 0, 0, and no, you don't have any products because the time is 0, the reaction did not started yet, started, right? And after 20 seconds, the reactant decreased from 1 to 0.54, and the product was produced from 0 to 0.46. And after the final timing here, you have 40 seconds. So the timing, the reactant A changed from 0.54 to 0.30, and the B, that's the product, increase the concentration from 0.46 to 0.7. Attention here that remember the conservation log, the mass, the conservation of the the mass conservation. The total here, what we have here, 1 mole, right? The second, here you have 0.54 plus 0.46, 1 mole. And after here, you have 0.30 plus 0.70, it is 1 mole. So the reactants are not being losing, they are being converted, right? They are being converted from reactant to product. Now let's calculate here the average rate at which EA disappears over the time from 20 to 40. Let's do here. So the rate, it will be minus 20 to 40. So final minus initial going to be 0.30 minus 0.54 divided by final minus initial, that is 40 minus 20. Remember, there's a here. So let's calculate it here. So should it be 1.2 times 10 to the minus 2 molar per seconds, right? That's right what we have here. So this second here, let's wait for the resolution improve a little bit. Okay, calculating an instantaneous rate of reaction. So you have time 0 here, right? It's asking calculate the reaction, calculate the instantaneous rate of disappearance of chlorobutane, butane at time is equal to 0. That's the initial rate. So let's take the slope here. You'll be this, the timing, and the concentration, right? Let's take this point here. Okay, no. So let's take the rate is equal minus the consumption of chlorobutane, butane, right? Divided by delta T is equal to the concentration range here is from what? 0.060 to 0.100. So let's go back ahead here. Do minus 0.060 minus 0.100 divided by, so the timing gonna be around it, let's see here, about 210, right? Minus 0, that was initial rate here, and minus 0. So here's molarity, and here for second, right? The final calculation here should be equal to 1.9 times 10 to the minus 4 molar per second. Sorry, molars per second. Okay? And for problem 3, practice problem 3, How is the rate at which ozone disappears related to the rate at which oxygen appears in the reaction 2O3 producing 3O2? So let's answer letter A here first. Rate is equal to, so the reactant, you have 1/2, because we have the coefficient 2 in front of O3, right? Changing in the concentration of O3 divided by delta T equal to 1/3 here, 1/3, change the concentration of O2 over delta T. So this is the answer for letter A. Use the coefficients in the balanced chemical equation to find this relationship between reactants and products. Now, the letter B asks if the rate at which O2 appears, it is 6 times 10 to the minus 5th molar per second at a particular instant, at what rate is ozone disappearing at this time? So you have the rate, the O2 appears, and is asking what's the rated ozone is disappearing at that moment here. So you have how we're gonna start. We're gonna start using this relation here between ozone and oxygen. So B, let's repeat what we will find in letter A. Right? So, and then you think, okay, but what's this? What's O2T over T? The change O2 over the delta T was given that should be 6 times 10 to the minus 5. So let's rearrange it here. So minus 1/2, if it's, you're gonna be rearrange it here. Let's arrange it, gonna be O3 over delta T. This one gonna be rearranged to be 2 to the third, right? Who is O2? The change O2 over delta T was given here. 6. Okay. So 6.0 times 10 to the minus 5th molar. So 2 divided by 3 and do the calculation here, times this. You should find it. Should it be what? Should it be 4 times 10 to the minus 5th here, molar per second. So sorry, here should be molars per second, right? Because it's the rate here that it came in from the rate of oxygen. This 230 here was just rearranged, right? From the 2 that it was here, and now was 2 divided by 3. Remember, the 3 came from the coefficient, O2 coefficient, and the 2 is because it's a coefficient of O3, right? So we should have this value here. Okay. Rate equation law. We have the reaction here, A plus B producing CD. A plus B, the reactant, CD, products. In the rate equation law, you're going to express the reactants only. So we have the rate, R for the rate, reaction rate, K for constant. It's the rate equation, the rate law equation. Sorry, rate law equation. We have R for the rate, reaction rate, K for rate constant, A are concentration species A, and B concentration of species B, and M for the order of reaction for respect to A, and N here will be order of reaction with respect to B. It is very important to know the order of the reactions. So determining find the concentration effect on rate. How do we determine what effect the concentration of each reactant has on the rate of the reaction? So let's see here the next topic. Here. An example of how concentration affects rate. So let's see here. Let's look at reaction experiment 1 and 2. Experiment 1 and 2, the concentration of ammonium double, right? But what's the table here actually? Raw rate data for the reaction of ammonium and nitrite ions in water at 25 degrees Celsius. So you have the reactants, you have ammonium and nitrite. The first one, you have concentration of ammonium changing and the concentrations of nitrite constant. And then you can observe what happens with the reaction rate. So for you guys to investigate what's happening with the reactants, one reactant need to choose the ones that the another reacts to be constant. For example, here, for us to investigate the rate, what's happening with ammonium, how ammonium is affecting the rate, need to choose experiments that nitrite is constant. For you guys to, if you choose the opposite, for you guys to investigate what's happening with how nitrite is affecting the reaction, you need to choose the experiments that the ammonium is constant. So for example here, to investigate ammonium, you can choose experiment 1, 2, and 3. Why? Because this 3 first, actually this 4, right? This 3 actually, this 3, nitrite is constant. And let's go to the opposite direction now. For you to investigate how nitrite is changing, how nitrite is affecting reaction rate, we're going to choose a 4, 5, and 6 because 4, 5, and 6, the ammonium concentration here, they are constant, right? Concentrations here. So let's go by step here. In experiments 1, 2, 3, the concentration of nitrite is constant. So any change in the rate here is due to the ammonium. So let's see here. As ammonium doubles, the rate doubles. right? For example, here, what's happening here? Doubles, and in here, doubles, right? So if you do this division here, rate 2 divided by 1. So rate 2 divided by 1, or divided by the second divided by the first one will be what? 10 times 10 to the minus 7 divided by the first one, that is 5.4 times 10 to the minus 7 equal to what? This divided by this, 0.0200 divided by so this one is going to be to the order, right? So let's see here. This divided by this is what? 2. And this divided by this is also 2 in case of the x. So to find how can you find x here? X is equal to 1. So what that means here? That means the order with respect to ammonium, it is first order. So let's write the rate law here. So we're gonna be like K one. So now let's do the same thing to find the rate of nitrite. So we don't know yet, right? Let's find it here. Let's choose the experiments that nitrite is changing, but ammonium is constant. Let's say 4 and 5. Can choose 4 and 5, right? So let's choose it here. What's happening here? Rate 5 and 4. Actually, 5 and 4. There is a typo here. 5 and 4. So rate 5 and 4. So it'll be 2.26 times 10 to the minus 7 divided by 10.8 by 10 to the minus 7 equal to 5 and 4 will be 0.0404 divided by 0.0202. Let's calculate the y. This divided by this is equal to 2. And this divided by this is equal to 2, right? Okay, check in the calculator to the y. So what value should it be y equal to? Should it be y equal to 1? Because 2 is equal to 2 to the 1, we're gonna be still. That means I equal to 1. So that means the order of nitrite is 1. First order, so the reaction is first order with respect to ammonium, first order with respect to nitrite, and the overall order of this reaction is equal to 2 to the second. Just to calculate the overall order, you do plus. So you calculate it here, right? The math becomes 2 to the y, so the order is 1. This is gonna be the rate law, which shows the relationship rate in concentration for all the reactants. So the order with respect to each reactant is 1. That means it is first orders in ammonium and first order in nitrite. And the overall order for the reaction is second order. So the reaction is second order because you needed to just adapt all the reactions order to get to overall reaction order. And what's K? K is a rate constant, and rate constant depends on the temperature. Rate constant depends on the temperature. Rate constant, it is a temperature-dependent quantity. Attention here, order does not equal stoichiometry. The order of the reaction must be determined experimentally. It's not necessarily related to balanced equation. Okay? And so, and you have here this table. So we have here relative value of K. The rate constant is often used to find the relative rate of a reaction. So usually like for K greater than 10 to the 9th, the reaction is considered fast. And usually for reactions with K equal to 10 to the 9th or lower, the reaction is maybe considered slow. But it's just a parameter here. So this table here shows what? If you have the reaction, the order for the reaction is 0. That means the concentrations of the reactants will not affect the rate. So that's why rate is equal to K. So, and to calculate the concentration versus time, the concentration versus time here, we can calculate it. The concentration, the time T is equal to the minus KT plus to the initial concentration. What that means? For example, if the order of the reaction is 0, you can calculate it how much, so what will be the concentration at a specific time? And you can calculate the half-life using this relation here. And the units, the K will be molarity per second. This for the 0 order. If it is first order, if you have rate, let's say that you just have one reactant, let's say for first order, right? Is equal, rate is equal to rate constant times concentration of A. And to calculate the concentration of A at a specific time, I'm going to use the natural logarithm. You've been using this formula here. And the half-life to calculate the half-life of a first order reaction, will be 0.693 to the divided by K. And the unit for first order reaction will be second to the minus 1. If it is second order reaction, let's say that you just have a reaction, one reactant, the A to the second here, rate is equal K to this A to the second. I'm going to be using this second, this to the second order reaction. I'm going to be using this equation here to calculate the concentration of A at a specific time. The half-life for second order going to be this formula here. And the unit going to be for second order for K, going to be molarity per minus 1 times second to the minus 1. Note that the reaction, not that is the reaction or the change the unit of the rate constant change. Can you see here? As the order changing, the units change. Okay. Okay. So let's stop here, right? We already stopped it for the lecture. Let's stop here, then continue here. For the next lecture.